All right. So, welcome to the end of May. It's our last week of May. We're cruising right along. Um, Hopefully, everybody had a good day off. Um, how's the homework going? Any questions about where we are and what we've been doing? Hopefully, that chapter 6 stuff was just really showing you why we care about solving second order differential equations. It's just a matter of plugging the right numbers in and specifically making sure you convert properly if necessary. Right?
I felt it was even easier than the earlier applications. I'm not sure if that was the case for everyone, but I just felt like it was more straightforward in a way. I mean, you don't have to derive the equations, so that helps, like with the in and out problems, but
Yeah, I think what it is that they literally are all the same form, right? Like it doesn't matter; they're all exactly the same, and you just put the respective values in to their right spots. So there isn't really a lot of thinking for these. Um, I think that's probably really the big difference. Because even like those mixture problems, yeah, it's always rate in minus rate out, but you kind of had to build them, and sometimes your concentrations change because the amount in the tank was changing and all that. So um, I think that's really probably where you're seeing that difference. But I agree with you, Thea. All right. Okay. Well, then let's keep going with where we were kind of getting ourselves set up last time, which is looking at power series solutions. So I want to start with a theorem telling you when we're good, and we'll actually start doing them today. So let's go to the board. All right. So first things first, let's go ahead and just write up here a generic differential equation. And this is going to be second order. So we're going to go with the homogeneous, so it's equal to 0. But let's just start with how we know when we have solutions and all that. Okay. So here's a theorem for you. So what we know is, let's say that P, Q, and R, these are going to be polynomials. So we're only going to be looking at the case where these things are polynomials. And I'm going to put here that all don't share a common 0. Okay, so it's okay for 2 of them to have a common 0. Like P and Q can have a common 0, Q and R can, whatever, but not all 3. Okay, so we're going to have these polynomials where there is no common factor. Okay, so then if x naught is such that P of x naught does not equal 0, then all solutions to this differential equation, they can be written as power series. And we know a little bit about their convergence. And we're going to say that they converge on at least the interval x naught minus r to x naught plus r. where R is the distance from x naught to the nearest zero of P of x. And I'm going to put here in the complex plane. Okay, so I just threw a lot at you. Let's talk a little bit about it. So I'll give you a second to write it down. Okay, so let's just kind of look at this again. So we got polynomials, they just don't share a common zero. And we just have to make sure that we're at a point where the P of x does not equal zero. We'll talk about what happens when we're at one of those locations. But if we're there, then we know that we can write everything as a power series, all solutions as a power series. And we know a little bit about its interval of convergence. Excuse me. Now, first, notice that I put at least. So what we have is a minimum for our interval. We can go at least r away from x naught, but it's possible we may be able to go further. But that minimum r is the distance from that x naught, wherever we're centering this, to the nearest zero of P of x. And I put here in the complex plane because it's possible that P of x has complex zeros. And in that situation, we do have to take into account the distance there. Do you guys remember the complex plane? Maybe a little bit. It's the ones where we've got the real numbers are left and right, like you're used to, and then the complex, the imaginary part goes up and down. So if you wanted to plot something like 3 plus 2i, you go over to 3 on the real and 2 on the imaginary. So just think of it like a regular coordinate plane, just with reals as your horizontal axis and imaginaries as your vertical.
Bruce, right from x naught the blank nearest zero. I can't read.
It should say from x naught to the nearest zero.
Oh, two.
It said the.
Oh.
Which was the fact that my writing is behind my speaking.
It was like there's like perfect glare there for
No
me.
worries. I got it for you.
Thanks.
You're welcome. Okay, so basically all this theorem is saying is when we're guaranteed a solution. I'm not going to prove it, but in this sort of situation, we are guaranteed solutions that are power series, and we'll know a little bit about where they're convergent. So this is necessary for us to even waste our time trying to do these things as power series, right? Because why would you do that if there was the potential that it wasn't going to work? Well, here we know it's going to work. Okay, so let's talk about this though, the P of x naught equaling 0. We have a name for those points where they equal 0 versus where they aren't equal to 0. And so let me go ahead and give you those names. All right. So x naught is an ordinary point if P of x naught does not equal 0. So those are called ordinary points. So basically, if you look at that theorem, we can just say, all right, it's going to work. We know there are going to be solutions at ordinary points. So if you've got an ordinary point, then that's going to be a place where we are guaranteed this solution in the form of power series. If P of x naught equals 0, we call it a singular point. And we'll see, not today, but we'll talk about this next time, which I guess will be next Monday, seeing we have an exam on Friday. We'll see that singular points we have to treat differently than ordinary points. Okay, so when we're at an ordinary point, it's all about just making the guess for our power series and seeing what that makes the coefficients equal. Okay, so the process is going to be, we're always going to start with y equals the sum from 0 to infinity of a sub n times x minus x naught to the n. On that x naught, that's going to be where we're centered. And so it'll either be told to you or it'll be clear from the context of the problem. Okay, but we'll know where we're centered. So we're always going to start with this. Then we're going to plug that into our differential equation. And we're going to see what kind of solutions we get. All right, so let's try one. I think I showed you kind of the basic steps with sine, or one that led to a solution of sine and cosine. But let's do another one that we know the solutions to, or that we could find them pretty easily. But let's go through this process just so you can see how it works. All right, so for this one, let's go with y double prime minus y equals 0. So like I said, this is one that you can solve. In fact, I bet some of you can just look at that and tell me what the fundamental set are.
E to the x.
So one of them is going to be e to the x, and the other one's going to be e to the minus x, right? Because when you make a polynomial, you get r squared minus 1. So there's no reason that we would do this the other way, or with power series, but I just want to show you that we're going to get the same thing. Okay, so we're going to start with this y, which means we need its derivatives. All right. I'm going to see if I can do this. I'm going to try to conserve some space here. So always in the corner, we'll have what y prime, and y double prime equal. Okay, so there's our y prime. We have to change the counter to start at 1. Then we get n times a sub n times x minus x naught to the n minus 1. And then the second derivative starts at 2. And then we're going to get n times n minus 1 times a sub n times x minus x naught to the n minus 2. So I'll try keep that stuff up there because we're going to use it every single time. You might want to write those down on a separate piece of paper so you reference it every single time you do one of these problems. Okay, so let's put these in. So we're going to get the second derivative So we're going to have n equal 2 to infinity, n times n minus 1, a sub n times x minus x naught. But I'll tell you what, let's center this at 0. Since we're not told specifically, let's just go ahead and use 0 to make life easy for us. So this will just be x to the n minus 2. Now we're going to subtract the sum from 0 to infinity of a sub n times x to the n. And I know that equals 0. Okay, so the first thing we have to do, absolutely the first thing we have to do, is start by making it so that all of these x's are raised to the same power. So we're going to do that shift. So I need to shift this by 2. So the way I'm going to shift it by 2 is I'm going to decrease my exponent, or sorry, my index by 2. So we'll start counting at n equals 0. And then I just add 2. So I'm going to put in n plus 2. So it'll be n plus 2 times n plus 1 times a sub n plus 2 times x to the n. So hopefully you remember when we were talking about doing that last time. But now I can go ahead and combine these into one. Since they both have x to the n, well, since both these sums start at 0, I can just combine those two things. They both have an x to the n, so I'm going to factor that out. So we get n plus 2 times n plus 1 times a sub n plus 2 minus a sub n times x to the n. Now, since this has to equal 0, that tells me that all of the coefficients have to equal 0. And since all of the coefficients have to equal 0, what I have now is a recursion relationship that basically says n plus 2 times n plus 1 times a sub n plus 2 minus a sub n has to equal 0. So whatever the a's are, they have to follow this pattern. I'm even going to solve that for a sub n plus 2. So basically, if you tell me some term in the series, this tells me how to find the one 2 down the line, right? So like if I know A1, this will give me A3. A3 will give me A5. A5 will give me A7. A7 will give me A9, and so on and so forth. Okay, well, yay. But now here's what we're going to do. We're actually going to figure out what these A's are. So we need to start with A sub 0, right? With our sum down here, we start with n equals 0. So we need to start with A sub 0. So what does A sub 0 equal? Well, the correct answer to that is whatever the hell we want it to equal. A0 is a free choice, but once we pick A0, then we're going to get A2, A4, A6, and so on down the line. Okay, well, let's start with A0. So what's A2 going to equal? Well, A2, that's what we get if we plug in 0 for n. So we're going to get 0 plus 2, 0 plus 1, which is 2. So we're going to get 1/2 A sub 0. All right, what about A4? Well, A4, we're going to put that, we're going to put a 2 in here for n. So we're going to get 1/4 times 3, which is 1/12. But it's going to be 1/12 times A2. A2, of course, was 1/2 A0. So we're going to get 1/24 A0. Well, let's keep going. A6. Now we're going to plug 4 in for n. So we get 1/6 times 5, which is 1/30. That's going to be 1/30 times A4. Well, A4 was 1/24 A0. This is going to be 1/720 A0. And we could continue going. I'm going to stop here for right now. All right, so far so good. All right, so you notice this gave us A0, 2, 4, 6, and all the odd, or sorry, all the even ones. So what about the odds? Well, for the odds, we got to start with A1. Well, what's A1? Again, the answer is whatever the hell we want. It's a free choice. But once we pick that, we're going to get the rest. So for 3, we're going to plug 1 in here. So we get 3 times 2, which is 6. So this is 1/6 A1. For 5, we're going to plug in 3. That's 1/5 times 4. So 1/20 times A3. Well, again, that was 1/6. So this is going to be 1/20. 1/120 of A1. And we'll do one more here. A7, we're plugging in 5. So we get 7 times 6, which is 42. So 1/42 A5. So we have to take 42 times 120. What is that? I don't even know.
5,040.
Thank you. Okay, and again, we can get all of the odds. All right, so now let me go back to what our solution looks like. And I've decided I'm going to get rid of this bit with the y prime and double prime. You guys all have it written down, remember it. But remember the whole point of these A's is they're giving us the coefficients on our power series. So here's what our solution looks like. Y is going to equal A0 plus A1 times X plus A2, so 1/2 A0, times X squared plus 1/6 A1 times X cubed plus 1/24 A0 X to the 4th plus, and so on down the line. So notice that all I'm doing is I'm taking these A's that we calculated and I'm multiplying them by X to the n. So there's the solution to this. Now, I know it doesn't really look at all like what we know the solution is, but here's what I want you to notice. I can actually break this into two pieces. Look at all the ones that have a naught. If I factor those out, I get 1 plus x squared over 2 plus x to the 4th over 24 plus x to the 6th over 720 plus ... And then I can add to that one that has all the A1s. And so that's going to be A1 times x plus 1/6 x cubed plus 1/120th x to the 5th plus 1/50/40th x to the 7th plus ... And each of those things in parentheses can be written as a power series. So I'm going to get A naught times the sum from 0 to infinity. And notice what the pattern is. On top, we're getting even powers. So we'll have x to the 2n. And on the bottom is always that factorial. The A1, same kind of story, except we're only getting the odds. So that means we need x to the 2n plus 1. And on the bottom is all of those factorials as well. All right, so this right here is a function in our fundamental set. It's whatever this is a power series. The other one, this guy right there, there's our y2. So we just found a fundamental set, but we found those functions as power series. Now, it turns out that those are not e to the t and e to the minus t, but they're linear combinations of them. They're just linear combinations of those that are also linearly independent. And so you may remember from linear algebra, and I apologize, Monty, but from linear algebra, we know that a basis isn't unique. And so we're seeing the same thing here. This fundamental set isn't unique. It just has to be the right size of linearly independent functions. All right, so there is no way in a million bajillion years that I would tell you to solve this one using power series. Because remember, first and foremost, I'm lazy. And every good mathematician is going to do things the fastest possible way. Well, in this case, this is not the fastest possible way. Right? But it is really nice to show you how this process works. We end up with nice functions so that when we make it a little bit more complicated, you can see how we can go about this.
I have a question.
Yeah, sure, Thea, go ahead.
So if we knew the power series for the 2 bits of the homogeneous solution of this, could we just technically plug that in and say it's being multiplied by some constant?
Yeah. I mean, that's what we did here, right?
Yeah, yeah. No, but I mean, like, okay, so we know the power series for each of the x.
Oh, I gotcha.
Yeah,
Good.
yeah.
So let's say, this is obviously an aside kind of thing, but
Yeah.
if we had really done this and we saw that y1 was e to the x and y2 is e to the minus x,
Yeah.
then yes, we could absolutely rewrite those as their respective power series. So like
Oh, sweet.
y1 would be the sum from 0 to infinity of x to the n over n factorial.
Yep.
And then y2, oh, that just died. Y2 would be the sum from 0 to infinity of minus 1 to the n,
Yeah.
x to the n over n factorial. This pen also just died. But yeah, we could have written the original as C1 times this plus C2 times
Yeah.
the other.
So on a test, if we saw that, oh, it's this function or whatever, and we know the power series for it, and we know both power series for each bit of the homogeneous solution, could we just plug that in and multiply it by some constant?
Instead of going through the whole process?
Yeah.
Yeah. But I'm not
Cool.
gonna have you do it on an exam for
Yeah,
a function that you can just solve otherwise.
got it.
Right?
That'd be too easy.
No, that's just busy work for the
Yeah.
sake of busy work. Right? We're not going to use this power series stuff unless we need to.
Got it.
Okay. So at least that's my philosophy.
Yeah.
I mean, obviously not everybody thinks like me, but I'm not a let's do work just for the hell of it. If especially in a class like Diffie-Qs where we're just trying to learn techniques for solving, well, you use those techniques when you need to use those techniques. Right. So with that said, let's change this differential equation ever so slightly. So now let's make it y double prime minus xy. Oh, actually, real quick, we want to go back. In terms of interval of convergence, remember what we had to worry about. We know that we're good at least as far as the smallest distance to a 0 of our p of x. Well, p of x here is 1. 1 has no zeros, so we know that this is actually good everywhere. This will converge everywhere. We're going to see the same thing happen with this differential equation, that what we find for our power series are going to work everywhere. Again, because it's 1 y double prime. I'll show you another example in a minute where we do have to worry about that. Okay, so notice that this is just slightly different. There's an x, and that's it. But that x means everything. Everything. Because now, if I were to ask you, what's a solution to this? And let me just say, non-trivial solution, just to keep Wes from saying 0. Okay, does anybody see a non-trivial solution? Okay, good. I didn't expect that you could, but it's not terrible, right? This is not the worst differential equation in the world, and yet we're kind of toast. So let's go to the power series. Let's see if we can construct at least the first few terms of these things and see what we get for our fundamental set. All right, so let's put them in. The second derivative is going to start at 2 and go to infinity. Excuse me. And we're going to get n times n minus 1 times a sub n times x to the n minus 2. Excuse me. And again, let's center it at 0 just to make life easy. All right, so we got this. And then we're going to have minus x times the sum from 0 to infinity, a sub n times x to the n equals 0. Excuse me. You guys are going to get really good at rattling off the forms of y, y prime, and y double prime. All right, so now we want to combine these into one sum. So I'm going to start the same way that we did before, where I want to get these powers of x matched up. All right, but excuse me, the place where I actually need to start is by taking this x and bringing that in. So any polynomial you have that you're multiplying, you want to bring that stuff in. So this is now going to be the sum from 0 to infinity of a sub n times x to the n plus 1. All right, so far so good. Now, this is a little bit different than what we did before, because now I actually want to shift this guy, and I'm going to shift this guy so that it looks like the other one. So how far do I have to shift it?
You'd have to shift it 3 to the right.
Yeah, I'm going to have to shift it by 3. All right, so if we shift it by 3, this now we're going to have, well, you know what? No, here's what we're going to do. Let's shift them so that they're both x to the n. So I'm going to shift this one by 2. We'll go from 0 to infinity, n plus 2 times n plus 1 times a sub n plus 2 times x to the n. And then the other one, I'm going to shift it 1, but I'm going to shift it the other way. So that we're going to get a sub n minus 1 times x to the n. I think this will be easier if we just have both as x to the n than trying to deal with some sort of weird x to the n minus 2 or x to the n plus 1 or something like that. All right, so here's the first kind of difference, is that you notice that we had to deal with changing the index on 2 different series, and that will happen. Sometimes you'll end up having to shift it on 3, all 3, right? It just gotta kind of play that by ear. Okay, so now we want to lump those sums together. But there's another problem here. Do you see what it is?
Isn't it that the indices of the starting indices of the sums are different?
Yep, that's exactly the problem. These do not match. And the only way we can put these together is if they do match. All right, so here's what we're going to do. We're going to play a little trick. I'm actually going to start with the one that's lower, and I'm going to start plugging those numbers in.
Oh,
Oh, tricky little buzzer, right? So let's plug in 0. That's going to give us 2 times 1 So 2 times a sub 2 times x to the 0. So it'll just be 2 times a sub 2. But then all the rest of them still follow that same pattern, starting with n equals 1. And so now I can combine these. So this is a trick that we will pull a lot. When we've got extras, well, we'll just plug them in until we match. Like, let's say the second one, it started at n equals 2. Well, if that had been n equals 2, we would have plugged in 0, then we would have plugged in 1, and then we could have combined the rest.
So it's sort of like when we would do the ratio test of like taking portions of the factorials out so that they were at the same spot, basically, so we could cancel them in a way.
Yeah. All right. So now let's look at where everything is falling out. Because we do have a recursion relationship, and we also have this guy right here. Okay, well, first of all, this piece. This 2a2, I know that has to equal 0. Because that's the only constant part of all of this. And since my total has to equal 0, I know that equals 0. But then I also, from my recursion relationship, get that a sub n plus 2 is going to equal 1 over n plus 2 times n plus 1 times a to the n minus 1. So that was just taking this and setting it equal to 0. All right, but now we're going to be ready to build everything. So let's look at what happened. So first of all, let's start with A0. So A0 is a free choice. I can let A not be whatever I want. Similarly, A1 is a free choice. It can be whatever we want. Let me write it next. Now, A2 is not a free choice. What does A2 have to equal?
0.
Has to equal 0 from this right here. So there is not going to be an x squared term in our solution. All right, so let's go to A3. Now to get a sub 3, we're going to plug 1 in here for n. So that's on the bottom going to give us 3 and 2, which is 6. So this is going to be 1/6. Now when n is equal to 1, that makes that a sub 0. So A3 is going to be 1/6 a sub 0. A4, we're going to plug in 2. Well, that's going to give us 1 over 4 times 3, which is 1/12. But then it's going to be 1/12 A1. If I want A5, I'm going to plug in 3. So it's going to give me 1 over 5 times 4, which is 1/20th, times A2. Well, A2, of course, is 0, so that makes A5 0. And here's what's going to happen. These are going to cycle through every 3 because these two indices, or the two terms, are off by a total of 3. So A6 is going to be related to A3. A9 is related to A6, A12, and so on. And so we're going to see the same kind of thing happen as before, just we're going to get one column of 3s. So A6 is going to be 1 over 6 times 5, so 1/30th times A3. So 1/30th times 1/6, which is 1/180th. A0. A7, well, it's going to be 1 over 42 times A4, which was 1/12th. A1, which I think is 464. No, not even close. 420.
504.
504, thank you. So 1 over 504. A1. A8, of course, is going to equal 0, and we can kind of follow that process. All right, so let me show you what this looks like, at least the first few terms. We're going to get y is equal to A0 plus A1 times x. There's no x squared. We're going to get 1/6 A0 times x cubed plus 1/12 A1 times x to the 4th. There is no x to the 5th. X to the 6th will be 1 over 180. A0, x to the 6th, I'll put dot, dot, dot. But we're going to keep following that process. But just like before, we have 2 that we can factor. We can split this into those with A0 and those with A1s. So this is what our solution ends up looking like. It's going to be A0 times 1 plus 1/6 x cubed plus the next one's 1/180th x to the 6th plus, and then more, and then plus A1 times 1 x, so x plus 1 over 504. Nope, hold on. What was our x to the 4th? Was it 1/12?
It was 1 over 12.
1/12, okay, thank you. 1/12 x cubed plus 1 over 504 times x to the 5th plus 7 plus dot, dot, dot. Okay, so now these, unfortunately, don't follow a nice pattern. I mean, they kind of do, but not really. Like the bottoms are almost factorials, but not quite. Like this is 3 factorial. This is, oh, hold on. I did something wrong. That should be 4. Right? So this one has parts of 4 factorial. It's 3 times 4. We're off by a factor of 2. But basically, we just keep putting on another pair of numbers in the denominator. Like this was 2 times 3. This was 2 times 3 times 5 times 6. The next one's going to be 2 times 3 times 5 times 6 times 8 times 9, and so on. But since there's not a nice pattern, this is how we'll leave it. And so you would say y1 is, well, this is y1. You would leave it like that. And this is y2. And it's usually at about this point that we all kind of feel a little like, what? That's it? It's a little anticlimactic, right? We want to be able to write, this is some nice series. But the reality is, way more often, it will be something where there isn't a nice pattern. You're used to always seeing a nice pattern because we were nice to you in calculus. We gave you the ones that always had nice patterns. But out there in the real world, they can look like just about anything. Ugh. All right. But this is what we're up for. We're looking for things kind of following this process. All right, so questions on that one? It all comes back to that recursion relationship. You need to figure out how these things are related, and you do that by getting the sums so that we've got x to the same power, and those sums have to start at the same index. Well, all we did was introduce an x. That's it. Just an x, and it made it that much uglier. In terms of interval of convergence, we know that these are going to converge everywhere because, again, the p of x, the polynomial on y double prime, has no zeros. So we know that it's good everywhere. Okay, well, the next example I want to show you is actually the same differential equation. We're going to solve that same differential equation, but I'm going to change the center. I'm going to make it so that instead of centered at 0, we're going to center it at 1. Okay. So before I do that, though, any last questions on this guy? All right. So ever so slight change. Barely changing it at all. We're going to make it so that now x naught is equal to 1. Well, here's where this changes things. Again, now our derivative, we're going to start from 2 to infinity. Still going to have an n times n minus 1 times a sub n. But now it's going to have x minus 1 to the n minus 2. And similarly with the other one, it's still going to go from 0 to infinity. It's going to be a sub n, but now it's going to be x minus 1 to the n. All right, so far so good. Ever so slight change. But this is going to make our algebra oh so much worse. Because remember what we did first last time? What did we do last time when we were solving it when it was centered at 0? What was the next step after we put in the series?
Didn't we correct the series so that they started at the same point?
We did something else first. It's a step that was so obvious that you probably don't even think about it. But we brought that x in.
Oh.
Right?
Eesh.
So we had x times x to the n. Well, here's the problem. Having x times x minus 1 to the n doesn't help us. What we actually need there is an x minus 1. Yeah. So here we go. I'm not going to touch this first one for a second. But here's what I'm going to write. I'm going to write this as x minus 1 plus 1 times the sum from 0 to infinity. So x minus 1 plus 1, that definitely still equals x, right? So what I really did, and you guys can grumble and complain, but remember, it's not me. Although I did pick this example. I've made it so that we now have 3 series. because we're going to have the one that we get when we distribute the x minus 1. So that'll give us x minus 1 to the n plus 1. And then we also have the one when we distribute the 1, which means we don't actually change it. So this is another reason why we tend not to center things off of 0, because then it makes it that much more difficult to do the algebra. But sometimes it's going to be necessary to center it somewhere else. But as this is, there we go. All right, so let's do the same thing. Let's change all of these things so that they all have a power of n. So we'll just shift them. So this first one will shift down by 2. So we'll just put n plus 2 everywhere. So we'll get n plus 2 times n plus 1 times a sub n plus 2 times x minus 1 to the n. The next one, we have to shift by 1 upward. So that's going to give us the sum from 1 to infinity of a sub n minus 1 times x minus 1 to the n. And then the third one, we don't have to shift it at all. But now all those powers are n. But we're actually in that same situation that we were before, where they don't all start at the same place. So we'll make them start at the same place by bringing all these up to 1. So I'll start by plugging in 0. When I plug in 0, I'm going to get 2 times a2. But now I'm also going to plug in 0 here, and so I get minus a naught. And then the rest of it we can write as a single sum starting at 1. And so we're going to get n plus 2 times n plus 1 times a sub n plus 2 minus a sub n minus 1 minus a sub n. All right. So now let's look at what our recursion relationship tells us. So from this first one, we're going to get that 2a2 minus a naught has to equal 0. From the other one, we're going to get, I'm going to solve it for a sub n plus 2. A sub n plus 2 is going to equal 1 over n plus 2 times n plus 1 times a sub n plus a sub n plus 1. So what's a little bit different here that we haven't seen before is that one of the n's is now going to depend on the two previous a sub n's. Okay, so let's look at what happens here. So a0 can be whatever we want. We're just going to call that a0. a1 can also be whatever we want. Right, a1 equals a1. a2, from this relationship right here, tells me a2 is 1/2 a naught. So now a3 is going to come from here. That's going to give us 1/6 the sum of A naught, no, not A naught, I apologize, A1 plus A2 nope, hold on, I botched this. This should have been N minus 1. So I was right. It should be A1 plus A naught. So then A4, that's going to be 1/12 the sum of A2 plus A1, which is going to be 1/12 times 1/2 A naught plus A1. I'm going to replace back in for A2. And so on and so forth. So let me write out the first few terms of the series. And then we'll split it apart and we'll look at what y1 and y2 are. So we're going to get y equals A naught plus A1x plus 1/2 A naught x squared. Yeah, that's A naught, A1, A2. Then we're going to get plus 1/6 times A1 plus A naught x cubed plus, I can fit one more here, 1/12 times 1/2 A naught plus A1 x to the 4th plus dot, dot, dot. So that was just this thing. And now let's pull it apart. So we're going to get A naught times 1 plus 1/2 x squared plus 1/6 x cubed plus 1/24 x to the 4th plus dot, dot, dot. And then plus A1 times x plus 1/6 x cubed plus 1/12 x to the 4th plus dot, dot, dot. And I made a mistake. It's not a terrible mistake, but it's something we have to go back and take care of. Anybody see what I didn't put in that I should have? I'll give you a hint. Where was this centered?
Oh, x minus 1.
Yeah, these should all be x minus 1. I'll correct it right here. So we're going to get 1/2 times x minus 1 squared plus 1/6 times x minus 1 cubed plus 1/24 times x minus 1 to the 4th, dot, dot, dot. And then similarly here, x minus 1 plus 1/6 x minus 1 cubed plus 1/12 x minus 1 to the 4th plus. All right, but again, there is no pattern to these. I know this one looks like we're getting factorials, 2 factorial, 3 factorial, 4 factorial. That pattern dies on the next guy. But the point of this is we centered it somewhere else and it made it way more complicated. And this little bit at the end, this mistake I made, of course, was done on purpose to remind you to always pay attention to where your center is, so that when you build your power series, you make sure you put the x minus that center. And I know you all believe me that that was done intentionally. that's bullshit, but we're going to go with it. The lies your teachers tell you.
So the lesson is hope for Taylor series.
Hope for centering it at 0. Yeah. Okay. So you may have noticed that there is one thing that we haven't done yet that we probably should talk about. Because what else sometimes comes up with these problems?
Convergence.
Okay, well, yeah, convergence issues. We definitely need to talk about that. But just differential equations in general. About an initial value problem.
Oh.
Right? So far, I haven't given initial value problems. When it comes time for initial value problems, they're going to determine the A0 and A1. These guys are our C's, right? When we used to call them C1 and C2, now we're going to call them A0 and A1, right? Or whichever two are the unknowns, because sometimes they're determined. But these are now our free choices. We still need to find those. Okay. So you might be going, well, that's really going to suck, because we're going to have to plug those X's in and figure out what's going on. Well, it kind of sucks, but not really. Because what if, for example, I had given you an initial condition on this? What if I had said, okay, so y of 1 is equal to 2, and y prime of 1 is equal to 0, right? Like, what if I had told you this? Think about what our process is. Now we're going to take, say, R1, plug it into the function, see what we get out. Well, check this out. If our initial conditions are where our center is, look at what happens when I plug it in. If I let x equal 1, then almost everything goes away, right? All of this stuff on the bottom disappears. All the stuff on the top disappears except for A1. And so y of 1 is actually just equal to A0 in this case. Similarly, if I were to differentiate, notice that on top, when I take a derivative, everything's going to have an x minus 1 in this first piece. So all that's going to go away. In the second piece, when I differentiate, all right, so this x minus 1 is going to give me a 1. Everything else is going to go away. And so in this case, that's A1. And so the key here is that if you have an initial value problem, that's where you pick the center. Okay, so let me just write this down as a statement of fact, or what you wanted. It's not fact, but it's going to help you best case if possible. All right, so given y of x0 equals, whatever, an initial condition, center at x equals x0. So remember when I told you that when you do this, you either pick your center or it's kind of clear from context. This is where I'm getting at clear from context. An initial value problem will tell you where you should center. So let's do one. And this will be the last one we do. I know that these are pretty brutal. So let's do one more with an initial condition. And this will tell us a good place to pick for our center. All right, so let's say we've got 2 plus x squared times y double prime minus xy prime plus 4y equals 0. And then I'll give you as initial conditions, y of 0 is equal to 1, and y prime of 0 is equal to 3. So that bit in red, ignore it. We don't really care about that for a while. So let's start the way that we always do with our sums. So we're going to get 2 plus x squared times the sum from 2 to infinity, n plus 1 times n times a sub n times x to the n minus 2, minus x times the sum from 1 to infinity, n times a sub n times x to the n, plus 4 times the sum from 0 to infinity, a sub n, x to the n. Now, the one thing that what in red told me was to center it at 0, which is why I'm just using x to the n. Okay, so now let's distribute these and create all our different sums. So we're going to get 2 times the sum from 2 to infinity of n times n plus 1, a sub n, x to the n minus 2, plus the sum from 2 of n times n plus 1, a sub n, x to the n, because that x squared cancels there. The next piece I'm going to get minus the sum from 1 to infinity. Oh, that should be an x minus 1, or n minus 1, sorry. So when we multiply that by x, that's just going to give us the sum of n times a sub n x to the n. And then the last one, of course, is still what it always has been. And this one's actually pretty nice. Notice that 3 of them are already all x to the n. So the only one we're going to have to shift is this first guy. And we just need to shift it by 2. So when I shift that by 2, it's going to start at 0, but it's going to be n plus 2 all these plus 1s are supposed to be minus 1. Sorry about that. So we get n plus 2 times n plus 1 times a sub n plus 2 times x to the n plus all the rest. I'm definitely running out of steam here. So that's this guy. All right, but now all of them start, or all of them have x to the n. But they don't all start at the same place. We got a couple that start at 0, another one that starts at 1, this last guy that starts at 2. So we got to start plugging stuff in until they all become 2. So let's start with the zeros. The zeros, this first one is going to give me 2 times a sub 2. The other one with a 0 gives me 4 a sub 0. So those are the bits with 0. The bits with 1. Okay, well, we plug in 1 here. So we get 3 times 2, which is 6 a sub 3. The 1 here gives me 4 a sub 1. And plugging 1 in here gives me minus a sub 1. So those are all the ones with 1s. And then the ones with 2s, and then on further, I'll get in my sum. So I'm going to get n times n minus 1 times a sub n minus n times a sub n plus 4 times a sub n plus n plus 2 times n plus 1 times a sub n plus 2. But all of that we can simplify. This is going to be the sum. Since these are all times a sub n, let's just lump them together. So we're going to get n squared minus 2n plus 4 times a sub n plus n plus 1 times n plus 2 times a sub n plus 2. All right. Well, let's at least get the first few of these A's. So A0 is a free choice. But then once we know A0, we're going to get A2 from right here. A2 is minus 2 A0. A1 is also a free choice. But once we figure out that one, we're going to get A3. Because A3 is minus 1/2 A1. So there's A3. Now, if we want A4, that's going to come from this recursion relationship. If I plug in 2 for n, I'm going to get 4 minus 4 plus 4, so 4A2. This one's going to give me 4 times 3, which is 12. A sub 4. I know that has to equal 0. So A4 is minus 1/3 A2. A2 was minus 2A0, so that's equal to 2/3 A0. And I think I'll do one more to get us A5. So I'm going to plug 3 in here. So we get 9 minus 6 plus 4, which is 7. So we get 7A3 plus 5 times 4 is 20. A sub 5. I know that's got to equal 0. So A3 is A5 is minus 7/20 A3. Well, A3 was minus 1/2, so this is 7/40 A1. All right, so now let's write out what our solution looks like. So we've got y equals A0 plus A1x minus 2A0x squared minus 1/2 A1x cubed plus 2/3 A0 x to the 4th minus, plus 7/40 A1 x to the 5th. So if we pull those apart, the bits with A0, we've got the 1 minus 2x squared plus 2/3 x to the 4th. The bits with the A1, starts with x minus 1/2 x cubed plus 7/40 x to the 5th. So this, we're doing exactly what we would have done had it not been an initial value problem. The only thing that's done for us so far is told us where to center it. But now we can figure out what A0 and A1 are. Again, y of 0 is equal to 1. If I let x equal 0, everything's gone except for the 1 A0. So from that, that tells us that A naught is equal to 1. Be careful. It's not always A naught, right? It's not always A1 with our derivatives. We have to be careful with that, but plug them in, see what you get. So then the y prime, think about what happens when we take the derivative. Up top, everything that's left is going to have an x, so that'll go away. Down here, the only piece that doesn't go away is this x. Its derivative is 1. So this equaling 3 does suggest that a1 equals 3. So because I'm lazy, let's just put that right there. And so here is your solution to this initial value problem. And it's not nice functions that we know, but we know it exists because this polynomial, the 2 plus x squared, does not equal 0 at this point. In fact, it doesn't equal 0 anywhere on the real axis. So we know it exists, and there it is. And obviously, in a real situation, like if this was a differential equation we were trying to solve for an applied problem, we would just go out as far in these polynomials as we felt we needed in order for it to do what we want it to do. Oh. So if you didn't hate power series before, you probably are now going to hate them because these are a pain. But you'll notice I did put up homeworks for 7.2 and 7.3, which are doing stuff with power series, but there's only like 4 questions in each set because I know they're brutal, so I'm not going to give you a ton to do. But before we call it a day, I want to talk about one more thing, and that is how far are we sure that these are convergent? What kind of an interval? Now, this one, that's a legit question because this polynomial no longer is constant, right? We've got p of x is equal to x squared plus 2. And so the question is, where are the zeros of this? Now you're going to have to be careful because you're going to look at that and you might go, oh, there are no zeros. And there are no real zeros, but there are complex zeros, right? If I take x squared plus 2 and set it equals 0, that's going to give me plus or minus the square root of 2 times I. And so if we were to look on the complex plane, here's where those are. So there's our complex plane. Plus root 2i is up here. Minus root 2i is down there. And so what we need to be concerned about is how far are those from our center? Well, our center was at 0. And so this distance is the square root of 2. Root 2i is root 2 away from 0. So then what that tells us about these series is that I know that these converge on at least the interval minus root 2 to plus root 2. It might be better than that, but I know I'm guaranteed at least we're good from minus root 2 to plus root 2. So that's how that whole distance away from the numbers on the complex plane plays out. It's all about plotting those points and then just figuring out how far you'd have to go. So obviously, if we centered this somewhere else, it'd be a different kind of distance, right? Like if we hadn't centered it at 0, but we had centered it, let's say, at -1, now we'd have to figure out those distances using the Pythagorean theorem, because we'd have a triangle whose lengths are 1 and square root of 2. and that would give us a distance of the square root of 3. And so now we know that that if we centered it at -1, we'd be good at least from -1 plus root 3 down to -1 minus root 3. Anyway. So I'm just going to leave you with this little pep talk. I don't know, word of advice. Word of advice here: slow, 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 slow. Do this slowly. Take your time. Watch your steps. Okay, there are lots of places where you can make an error, so go slowly. Do not try to rush through these. Rushing through these will only cause you problems. Okay, so go slow. Yes, they take forever. They are tedious. Yes. Okay, but go slow, watch yourself, catch any errors early before you go too far. All right, so in terms of the exam next time, so I'm going to stop here with power series. So the exam next time, it's going to be on chapters 5 and 6, right? So chapter 5 is all of the solving second order differential equations. And in there were 3 really big processes. The first, undetermined coefficients. That's where we look at what our function's equal to and we make our best guess, right? Like if it's an exponential, we make a guess of an exponential. If it's sine or cosine, we make a guess of sine or cosine, right? We put them on with just unknown coefficients, hence the name undetermined coefficients. And then you end up with a series or a sequence of, not a sequence, a system of equations that then you can solve. Okay, so there's that one. There's reduction of order. Reduction of order works when you know one of the fundamental set. So if you know one of the fundamental set, then you make a guess of a multiple of that, take some function times that, and go through and see what that has to be. Okay, so reduction of order. And it does exactly what it sounds like. It takes it from second order to first order, and first orders we know how to solve always. Okay, and then the third one was variation of parameters. And that's the one where you do need to know both of the fundamental set, right? So you need to have both elements of the fundamental set, but then you build the Wronskian matrix, right? And basically, we look for a solution that's of the form u1, y1 plus u2, y2. But there's a process. It always comes down to the same system of equations that involves that Wronskian. And that's how we can find our u1 and u2. So a big portion of this test is going to be having you solve using those different methods. Now, if I don't tell you a method, if I just say solve, that's up to you. Solve it however you want. However, I might say use variation of parameters, or I might say solve this using undetermined coefficients. If I do specifically tell you, make sure you do it the way that I ask, right? But other than that, I mean, you're free to solve it however you need to solve it. And sometimes there's one that's faster than the other, but you know, that's how it plays out, right? So that's chapter 5, and then chapter 6 was the applications. So that was the spring mass systems, the RLC circuits, where we now allow for drag and all that. And hopefully most of you are feeling how Thea mentioned right earlier today with the you know, it's not that bad. I mean, they're even easier than others. Hopefully you're just seeing it's a process. It's always the same thing, always the same thing. And the nice thing about those is that the form that they take on is easy to solve because it's always one that you can solve using, like you can find the fundamental set pretty easily by creating the polynomial and finding the roots, right? So luckily they're all really, really quick because they have constant coefficients once you get it set up, right? So the one thing I'm going to warn you about there is watch your units, make sure things match up, right? So displacements are always, like in metric, make sure displacements are always meters. Make sure times are always seconds, right? And then I'm gonna I'm gonna try really hard not to give you guys ones that involve pounds and stones and all of that, because those are nonsense units. All right, so I will try to make sure everything is in metric. So anyway, so that's what's coming. In terms of best ways to prepare, probably just practice a few of the different methods, make sure you got it down. When it comes to the undetermined coefficients, maybe not going all the way through, but at least getting yourself set up, right? The one thing I do want to mention about undetermined coefficients is watch out for when the form we want has fundamental set elements in it, because then we have to make sure we multiply by t, or at least multiply by whatever power of t we need to ensure that we're getting new things, right? All right. Yeah, so I think that's all I've got. You guys have any more questions about what to expect from the exam or anything else?
Oh, will you be asking like, oh, what's the period of this, or are you just gonna be asking, oh, what's the equation that shows the change?
I can't answer that because I haven't written
Yeah.
the test yet.
Got
Obviously, I am going to want to know like equations, right,
Mhm.
for position or
Yeah.
velocity, stuff like that. I might ask you for period,
Got it.
you know, and stuff like that. I doubt I'll ask for phase shift because phase shift's boring and kind of irrelevant because you just, you know, choose your time to be different and then you don't have a phase shift. But period and amplitude are definitely things you should be able to figure out. And where those get interesting are when we don't release from rest, right? That's where, like, you know, we pull the spring and then we push it up as we let it go. That will change your amplitudes and stuff like that. So it would be good to know how to do that. Maybe have those formulas handy, but they're pretty straightforward, right? I mean, it's the same process every time. You just have to plug in your right numbers.
Cool.
All right. Other questions? Well, all right. Well, then, as always, good luck on your test. If you need different arrangements for time, shoot me an email, remind me, and we'll set something up. And other than that, you guys have a great weekend, and I will see you all Monday.
See ya.